As Corey said, I am here to talk about Miniscript. This is something that I've talked about a few times before, but usually in a much more technical way, where I would kind of get into the weeds of Bitcoin script and what Miniscript is and how to use it and stuff. But I want to talk today about Miniscript from the perspective of somebody actually trying to use Bitcoin and how this solves problems that I think are very important in the space regarding how to custody your coins, how to keep track of your keys, stuff like that, basically. So before I jump into that, let me briefly introduce, so the structure of the talk is roughly, I'm going to talk a little bit about Bitcoin script for a couple of slides. Bitcoin script is a system built into Bitcoin that's used to define spending conditions for coins. Meaning, well, typically what that means is you'll have, for an ordinary wallet, you'll have a script that basically says to move these coins, a transaction needs to have a signature with a specific public key. So your script is really just like a thin wrapper around your public key. But you can do more interesting things using script. You can say, well, here's a list of 3 keys, and any 2 of them need to sign, and you can do like an escrow kind of 2 of 3 thing like that. You can check that a certain amount of time has passed before certain keys can activate. You can check that like hash preimages are revealed, and that's how Lightning HTLCs work. So there's all sorts of neat technical features that are accessible in Bitcoin script. But as I'll talk, there are a number of problems that make this in practice quite difficult to do. And as a result, the situation with Bitcoin wallets is that typically they don't really use script in any interesting way at all. And when they do so in ways that don't really interoperate with each other. And so what I'm going to demonstrate here is that there's another way to write scripts for Bitcoin, where rather than directly using Bitcoin script, you can use this thing called Miniscript that I'll explain, that gets you a framework for writing scripts, which is easy to reason about. And so I have these 3 words here: custody, computable, composable. Custody is what I'm going to focus on, like how do you hold your coins. Computable means with a Miniscript, you can reason about what your script is doing. You can figure out how much it's going to cost. You can do accurate fee estimations. You can determine semantic properties of your script. And what I mean by that is you can ask questions like, given some arbitrary, complicated script, could somebody use that script to move my coins without my signature? That's a question that you should ask for any complicated script. And prior to Miniscript, the answer was basically, I don't know, don't use script, right? Just like stick with something you know, stick with templates, stick with something you've analyzed. But with Miniscript, you can do kind of arbitrarily complicated things and still be able to answer questions like that. So I'll jump into that. And then the third word here is composable. And this is interesting. It's a bit of a technical word, but the premise here is pretty straightforward, which is that if you have a high-level spending policy and you want to replace some components of your spending policy with something complicated, in Bitcoin script, you can't do that easily, like verifiably. With Miniscript, you can. So an example of that would be, imagine that you're on the board of directors of some company that's holding a bunch of Bitcoin, and you agreed to do some sort of multi-signature policy. You need like 4 out of 5 board members need to sign to move the coins. And you're one of these board members, right? And so the rest of the team asks you for a public key, but you don't really want to give them a single key where there's some secret key somewhere that you could lose or whatever, for the same reason that you wouldn't want to keep your Bitcoins in an output controlled by a single key, right? You want some redundancy, you want some sort of resilience. And so ideally you could say, well, my part of this 4 or 5 is going to itself be a 2 of 3 keys that I have, like, custodied in different parts of the world under different rules or whatever. But with Bitcoin script, you can't really do that, right? And I'll talk more about why that is. But basically, if you were to if somebody asks you for a key and you reply with this complicated set of keys and rules for how they behave, the person receiving that and the other participants in this script are going to have a hard time verifying that what you're doing is okay. Because basically, what you're doing is providing a fragment of script, a fragment of computer code, and asking to insert that into the middle of a larger computer program in a model that doesn't really match the way that people think about spending conditions. So I have a couple slides here, basically like listing problems with script. And some of these are fairly technical and things that you really only care about if you're a wallet developer. some of these are things that everyone should care about. So in particular, the first two, right? What do you care about when you're creating a Bitcoin script, when you're defining a spending policy? You care that it's correct, right? Which means that the coins will move if they're supposed to move. And you care that it's secure, which means that the coins will not move if they're not supposed to move. And those two things are kind of difficult to express in Bitcoin script because script is just a low-level stack-based programming language. It's a set of like small instructions to the computer, or to all the nodes in the network, that say things like, well, move this data here, and then swap this data with that data, and then like add this data to that data, and then interpret this blob as a signature and check that the signature is correct with this other blob that you should interpret as a public key, and so on. It's just going like step by step by step, rather than thinking, what are the set of conditions under which the coin should move, right? Which is the way that people think about this, right? People want a set of spending conditions, and they want to verify that the script somehow represents exactly that set, no more and no less. Then the bottom 3 points that I've got here are ones that you care about as a wallet developer. And the reason that I list them is that this is basically the reason that you can't download an arbitrary Bitcoin wallet and do interesting things with it. Just like stick multi-signatures onto it, or attach like 5 different hardware wallets to it, or have a second cosigner or whatever. You need a wallet that specifically supports those things. And if you choose one, you can't really move your coins from one to the other without like actually sending them across the network, right? You can't like export a policy and import it somewhere else. And the reason is that as a wallet developer, when you're trying to implement these things in script, you need to figure out like how do you actually produce transactions on the network that use this script. And it turns out there's a whole list of technical problems that you have to solve. And basically you have to solve it independently for every single script that you create. So if you want to make an interesting wallet, you need to hire a team of Bitcoin experts to define a script that makes your wallet interesting. Then they need to do all this analysis. And then they need to solve a bunch of questions about how big will the transaction be, and how do you estimate fees, and if you have the signatures, how do you put them in the right order, and all these kind of annoying detailed questions that you need to answer for your stuff to work, but which really like you don't care about. It's not part of your business logic. And it would be better if this were somehow a solved problem. So then on a high level, zooming out, you get these 2 problems that I've been hinting at, right? The first is you get these 2 problems, interoperability and composability. So for those of you who can't see the screen there, it's just those 2 words as the entire slide. So interoperability is the fact that, well, as I mentioned, if you're using an interesting wallet of one form and you want to work with an interesting wallet of another form, you kind of have to pick one or the other. And to switch between them, you have to send the coins across the network. And if you want to do something like do a coin join, say, where you have 2 wallets, maybe you have like a BitGo wallet on one side and like a Blockstream Green wallet and then a Bitcoin Core wallet, and you want the 3 of them together to sign a transaction. That's pretty difficult. That's pretty difficult to do because those 3 different wallets have different script templates and they don't understand each other's scripts. And then relatedly, we have this problem of composability, where suppose we're back to this board of directors example, where I'm one out of 5 directors. We want 4 of those 5 to be able to move the coins. And I say, well, I don't want to give you a public key. What I actually do is I use BitGo for custody. Okay, so I'm going to give you this BitGo script that has like a 2 of 3 signature where only one of the keys is mine. And I want you to come out like fit that into this higher level policy. In Bitcoin script, you basically can't do it, more or less. So the idea here, the technical idea behind Miniscript, and I'm going to have some pictures for the next couple of slides, so this will maybe be easier to see. The technical idea behind Miniscript is that we could take all of the little things that you can do, all the individual functionalities of script that people use in practice, which are signature checks, they're hash checks, and they're time checks, basically. And the different primitive ways that you can compose these, so you can use AND, so like all of these conditions need to be satisfied, or ORs where only one of them does, or threshold, which are kind of in between, right? You say like 3 out of the 5 of these things need to be satisfied for the coins to move. And we can create these little short script templates that represent these. So now rather than directly working in Bitcoin script, we're going to work in this higher level language where the primitives that you're working with are things that have more meaning. And the cool thing here, I mean, that's not a novel idea, right? People have tried to make high-level languages for script a number of times. And there are two cool features of this. The big one here is that this isn't a separate language from script where you compile it down and you have a compiler that tries to interpret what your code means and then output a script that has the same meaning. With miniscript, there's actually a direct one-to-one correspondence here. So you can compile, you actually are just encoding your miniscript directly in script, and you can decode it as well. So you can see that what's on the blockchain is exactly your policy. You actually are secretly directly working with Bitcoin script. And the other thing is, the other difference between this and I guess what you might think of as a high-level language is that this isn't just like a friendlier way to write an imperative program. This isn't a friendlier way to tell all the nodes, do this, do that, do that, do that. And then if everything's okay, then let the coins move. The way that miniscript works is that you really are directly representing the spending conditions that you want to express. So here I've got a picture. On the left here I've got a Bitcoin script where I've added some indentations and colors to try to separate it. But it's really not a structured language, so I made some kind of arbitrary choices there. And on the right I have a miniscript, which represents the same thing. And these are actually exactly the same thing. And the miniscript, typically, if you're actually using it, you wouldn't have this nice graphical representation. You would have like a text string or something, but you could essentially read this tree structure here. So you can see what's happening here. I've got, it looks like 4 public keys in parallel. So at the top level, I've got this OR. So I have these 2 halves of the script, and I need one of them to be satisfied in order for my coins to move. And on the left side here, I've got this multi-signature, what I call a thresh M, which is just a says like, well, of the set of keys, some number of them need to sign off to move the coins. So on the left, I've got this 2 of 3 policy. And on the right, I've got this AND here, and I'm saying that 2 things need to be satisfied if you want to take the right branch. And the first is a signature with an alternate emergency key, and the final thing is this after 1000. And after 1000 is pretty cool. What that is saying is that the coins, this branch can only be used after 1,000 blocks have gone by, if the coins have not moved in 1,000 blocks. So the idea here is that I have this sort of like normal spending policy, this 2 of 3 policy, that under normal conditions I want to use to allow the coins to move. But if something goes wrong there, if 2 of the signers have dropped off or they've lost their keys or whatever, and the coins are unable to move, then after some amount of time, and it doesn't have to be 1,000 blocks, it could be a year, it could be until like some fixed date in the future or whatever. If the coins haven't moved in a long time, then this alternate emergency key should come online. And it can't be used until then, right? Because the point is it's an emergency key. And it possibly has a different trust model that you don't want to be active under normal circumstances. So you can sort of see on the code on the left, it would be very difficult for me to express that, like describe to you how the code on the left maps to the actual policy that I want. But with the code on the right, if I want to just zoom out and say, what is this doing? Really what I can do is just delete a lot of the extraneous stuff here. You see like in the miniscript representation, I've got these B's and V's, I've got some subscripts and so on. And those are just details. Those are really not so important to a user. They're important to a wallet developer. If I drop that data, now you can see I have this high-level policy here. And you can just see I've got an OR, I've got an AND. I'm directly representing my spending conditions as spending conditions. So if you are an auditor or you're just somebody trying to participate in a script like this, you can look at this and visually see that the script policy matches what you intuitively expect it to be. And so if you're trying to ask questions like, is it possible to spend these coins without my key? Well, you can look at this, right? So let's suppose that my key is PK1. Well, then I can see that there are actually a couple of ways these coins can move without my key. So the first is, obviously, if PK2 and 3 decide to sign, well, you only need 2 of those 3 keys, so my key doesn't matter. All right, that's good to know. And then the second is this emergency clause. But I can see on the emergency clause that it only activates after 1,000 blocks. So if my question is, well, what if, as long as things are going normally, is my key necessary? I have a much simpler question to ask. I can basically just hide that entire time lock section. And what's even cooler is that I can actually like do that automatically, right? I could just ask the computer, or ask a program designed to analyze these mini scripts, say like, well, what happens? What if it's the coins are only like 10 blocks old, and the computer can just drop everything that's contingent on their on time locks that are further than 10 blocks out? Or I can say like, well, what if my key is definitely present? Then what would the script look like? What remaining conditions need to be satisfied? What if my key is definitely not present? What conditions need to be satisfied? And you can sort of see that I'm going to get like very precise answers here. And if my goal is to assure myself that the script makes sense, that's pretty cool. And in fact, I can do that with an arbitrary script. I don't need to have a team of Bitcoin experts build this little tree on the right, because this is something that you could do with a fairly surface level understanding of how Bitcoin works, but maybe a detailed understanding of what you want your threat model to be and what you want the security policy for your coins to be, which is what you want, right? Because Bitcoin technical experts are not necessarily experts in your security model and vice versa, right? And ideally, you don't need to find people who are experts in both. And this also leads to solutions for my two problems here, right? Interoperability and composability. So interoperability kind of comes for free because, as I said, you can ask these questions in an automated way, just go through any script and get answers to them, which means we can write general purpose libraries, and we've written a couple, Peter and I. General purpose libraries that can answer questions like this. And then wallet developers can just use these and build wallets that will work with each other even when they're doing interesting stuff. And I think the major wallet that I'm aware of that's using this is a Spectre wallet, but there's a wallet library built on top of Miniscript called BDK that I think there's a workshop about today, which uses Miniscript under the hood to give your wallet all sorts of cool features. Then the second problem, of course, is composability. And you can almost see visually how this solves the composability problem, right? So if I'm supposed to be like a public key, if this one of those red squares was just like a public key representing Andrew, and I say, well, I don't want a public key, I want like a 2 of 3 script or something or other, I want some complicated thing. I can just replace my red public key square with an arbitrary subtree of other conditions. And everyone can verify that I've just replaced my own little part of the tree with my weird conditions. And so to give a final example of how this is useful before I move on, you can imagine someone like BitGo, whose business model is that they're a countersigner, or Blockstream Green, which does kind of the same thing but for retail customers, where their model is that they just sign off on every transaction that you ask them to sign off, unless you call them out of ban and tell them to stop, or unless they detect funny behavior on the network, or unless they see a double spend or whatever. They have some basic rules that they follow. But basically, from their perspective, they care that your coins are stored in a script that requires they sign, basically. And the way that both of these wallets do their thing is that right now they have fixed scripts that you have to use, right? Which is a simple like 2 of 3 or a 2 of 2 multi-signature script. But really, the only thing that BitGo cares about, the only thing that Blockstream cares about is that their key is necessary. So you can imagine one of these mini scripts where at the top level you've got an and then one branch of the and is their key, and the other branch is completely arbitrary. They don't even have to look at it. They don't, unlike Bitcoin script, where they'd have to read the whole thing and like say, are there bugs here? Like, can you override these other conditions, whatever. In Miniscript, when you see an and, then you know that both conditions have to be satisfied. So if you only care about one of them, or you're in control of one of them, you really don't care. Like, my signature needs to be present. And this would allow BitGo or Blockstream Green to both do like much more interesting and generic flexible things and allow their users a lot more freedom to do interesting things with their own keys, splitting up their keys, doing multi-signatures, things of this nature. So, as a final point, and this is a little bit speculative, but I want to talk from a technical, future-looking perspective. The cool thing about this Miniscript model is that, actually, let me reorder these slides a little. Let me just go to this slide first and just summarize what I've been talking about. And say, on a technical level, I've been talking about Miniscript like as a set of script templates, right? You just you have these red and blue boxes, and each one of them represents a few opcodes or whatever. But really, Miniscript is a different paradigm of script. It's a way of representing your spending conditions directly as these trees of spending conditions. And the way that I've summarized, I say that like Miniscript describes the conditions to satisfy rather than instructions to execute. And the cool thing there is well, certainly everything I've just talked about, right, like direct benefits for users of Bitcoin script, But another cool thing is that in principle, we don't need Bitcoin script to be what we translate miniscript into. We could have any language, really, that can express spending conditions. And as long as you can extract fragments of that language that represent these different ors and ands and thresholds and so forth, then you can translate that language, or some subset of that language, into miniscript and back. So the cool thing here is that if you have two systems that have completely different script systems, you can imagine like Bitcoin script versus Ethereum's EVM. In principle, you could write a miniscript backend for EVM, and then you could take a Bitcoin script, decode it as a miniscript, and then re-encode that as an Ethereum program. And now you have this set of spending conditions that you can express in the same way on Bitcoin and Ethereum, and you can verify that they're the same, and same going the other direction. And this is kind of a cool trick, and that by itself actually may be interesting to people who need to work with both of those blockchains. But the other interesting thing is that it doesn't have to be a deployed language, or rather, let me rephrase that. If we were working on extensions to Bitcoin script or replacements for Bitcoin script, which I am, I spend a lot of time thinking about blockchain programming languages, then I can use miniscript as a guide for what users are trying to do. So I guess there are two directions I can extend this. The first is thinking about replacing Bitcoin script, in which case I want to retain compatibility with miniscript. And in doing so, I allow existing users of miniscript, to just directly translate their stuff into my new language. And I can look at, well, how efficient is that? Like, what does that do to their fee rates? What does that do to the computational efficiency of various problems, of answering various questions about your script? So that's kind of cool. That means that I can start working on iterations, working on improvements to the underlying Bitcoin script system. And rather than thinking, well, script was already a nightmare for people to use, and I'm going to ask them to learn this whole new thing, I can say, well, miniscript provides them a direct migration path. And not only, so as a developer, I care about people using my stuff, so I care about there being a migration path. For users, what they care about is that they can try my thing and then go back, right? They're not committed to learning a whole bunch of stuff. And miniscript, because it's not a compiled language, it's really just a reinterpretation of the underlying script, lets you do that. You can take a Bitcoin script, interpret it as miniscript, reinterpret that as EVM, or reinterpret that as simplicity, or reinterpret that as whatever future thing, and then go back. And so you not only have an easy way to back off, but you also you can